Before the advent of automobile, people traveled by horse, cart, or horse-drawn carriage, bicycle, train, and ship. In 1885, German engineers Karl Benz, Gottlieb Daimler, and Wilhelm Maybach built the first gasoline engines, and in the next year, Karl Benz filed a patent for a three-wheeled vehicle driven by the gasoline engine, and thus gave birth to the world's first motor car, or automobile. Now let's come with me to the Mercedes-Benz Museum in Stuttgart, Germany, and take a look at some awesome cars from different decades in history. When you look at the following cars, pay special attention to the changing trend of their shapes. From the 1904 Mercedes Simplex, which has a top speed of 50 miles per hour, to the 1955 Mercedes-Benz, which has a top speed of 180 miles per hour, we can see that the top speed has nearly quadrupled, and the frontal area has become much smaller. Why do you think engineers made the car look so much thinner from the front? Does the new design have something to do with the speed of the car? To answer those, we'll have to discuss a little bit about air resistance, which is also called drag. Drag is a force which opposes the movement of an object. Imagine a car that's moving horizontally to the left. Let's draw a free body diagram to analyze the forces on it. Vertically, there's always the force weight, which is equal to mg. Then there's the normal force. Horizontally, there must be a force that is pushing the car forward, and let's call it force 1. Finally, there is a drag force, which is opposing the movement of the car. So, what exactly is drag? Why don't we do a very simple experiment now? We only need two identical sheets of paper with the same mass. Let's call them M1 and M2. Make one of them into a paper ball, and leave the other one clean and flat. Even though their shapes changed, they still have the same mass, and so the Earth exerts the same force weight on them. Now stand up and drop them to the ground from the same height and at the same time. Which one falls to the ground first? If we did the experiment in vacuum, they will fall to the ground at the same time, but we're doing it with lots of air around us. Since air is also a fluid, we cannot ignore the resistance force that air will exert on moving objects. We see that the paper ball falls to the ground first, while the flat sheet of paper is still swinging its way down. Since the paper ball fell to the ground first, we can assume that the vertical net force on the paper ball must be greater than the vertical net force on the flat sheet. To make things easier, from now on I will say everything in letters and numbers, and 1 means paper ball, 2 means flat sheet. We know that F weight 1 is equal to F weight 2, and drag is vertically upward, opposing the downward movement of mass 1 and mass 2. Since the net force is equal to F weight minus F drag, and F weight 1 is equal to F weight 2, the only way to come up with a big net force is to have a small drag. So F drag 1 must be smaller than F drag 2. With those in mind, we can now theoretically prove why M1 or the paper ball landed first. They fell from the same height above ground, so their distance of travel is the same. Let's call it x, and let's call the time of travel t. We know from Newton's second law that F net equals mass times acceleration, and also from some kinematic equations, x is equal to 1/2 at squared, so t is square root of 2x over a. Since F net 1 is greater than F net 2, and F equals ma, so a1 must be greater than a2. We plug a1 and a2 back to t equals square root of 2x over a, and get t1 is less than t2, which literally means m1 lands first. But why did the paper ball have a smaller drag? Look at the formula for drag. Fd is 1/2 rho v squared c sub d times a. Rho is the mass density of the fluid, v is the speed of the object, c sub d is the drag coefficient, and a is the reference area. It actually has nothing to do with the mass of the object. Instead, it has a lot to do with the speed and shape of the object. So even though the paper ball and the flat sheet have the same mass, their different shapes will give them different amounts of drag. There are different types of drags, like parasitic drag, which consists of form drag, skin friction, and interference drag. There is also lift-induced drag and wave drag. But now let's just look at form drag, which relates the shape of an object with the amount of drag it gets. Look at the diagram. If airflow is blocked by a big surface or funnel area, then you'll get a lot of drag, and vice versa. That explains why the paper ball doesn't get so much drag as the flat sheet of paper. And it also explains why engineers over the decades have made automobiles look so much thinner from the front. From the drag formula, we see that the speed is squared. That means if you're driving at low speed, you won't experience as much drag as if you're driving at a much higher speed. Over the years, cars have been made to travel at higher and higher speeds, meaning that they will experience more and more drag. So in order to have less drag at a certain speed and in a certain fluid, in our case, air, you'll need to make the reference area as small as possible.